we'll be doing 4.4. And related rates are things that change as other things change. That's why they're called related rates. They are rates of change that are related to each other. For example, if I were to have a cylindrical swimming pool in my yard and I call the fire department to start filling it up with water, there are things changing as other things change. As the volume changes, so does the height. Correct? As the volume changes, the radius doesn't. So sometimes things don't change, but sometimes they do. That's why they're called related rates. Now, if I have a conical sand pile and I am removing sand from it, or gravel in a gravel pit, lots of stuff will be changing, right? The radius will go down as the height goes down, as the volume shrinks, all of it. So sometimes things are changing and sometimes they aren't, and it's our task is going to be to figure out missing rates of change. I'm going to skip that first part because I don't know that it does anything in the long run. So we're going to start off, first of all, just getting these statements into calculus notation. This word rate and the word increasing, the word changing, shrinking, growing, those indicate rates of change. We're going to be setting them up and we're going to be finding them. So use variables that make sense. dy dx, we should probably not see at all this chapter. Okay, that's what we use when we had just our generic functions. Y was f of x, y equals sine x plus whatever. Right now, it's not going to be x that's changing anymore. Most of the time, not always, the thing that will be independent or causing the change will be time. So what do you think is going to be on the bottom of all of these? dt. Yep, all of these are changing with respect to time. Does that mean every single problem we do is going to have a dt on the bottom? And the answer to that is almost. Every once in a while, like we had one in BC recently where there was a plane flying and taking off, and we said, well, how is its distance from the airport changing as the angle changed? So we weren't doing it as time went by, we had the angle growing, which it would cause, you know what I mean, it causes a change in the distance, but usually it's time on the bottom right there. So on the top, use something that makes sense to you. For John growing, maybe dh dt for height, or dj dt so you know it's John. When things are growing or increasing, we use positive numbers. So that's the first task, is really easy. We're just going to be getting out of dy dx, and I wish this would erase. Maybe it will with my hand. Oh, there we go. Out of dy dx and contextually. So over here I've got my mutual fund shrinking. So I'm putting money in a fund and that fund is decreasing in value. So I maybe on the top might call it dm dt for money or mutual fund. That's up to you what you call them. But you're going to have multiple ones within the same problem. So you see the issue of calling them dy dx? You're not going to know what they stand for. So if it's a radius, like call it dr dt. If it's a volume, call it dv dt. If it's a height, call it dh dt. All right? And then keep track of whether things are increasing or decreasing. Shrinking is going to be a negative rate of change. This guy right here is increasing, so it'd be a positive rate of change. And my volume right here is decreasing, so it'd be a -2 for my rate of change. So you're going to be setting those up, and you're going to have multiple ones within the same problem. Does that make sense? So we're going to start really slowly. If you go ahead and page ahead to where you see a list of all the steps, it can be kind of daunting because this is what you need to know how to do. But it makes so much sense. Like, I don't even think you'll be looking at these steps. That's why I put them after we do it, because if you kind of follow the same workflow, they're super logical, even though that looks like a lot, doesn't it? Every problem, you have to do all of that. It looks like a ton. It's not as bad as it looks if you kind of approach them all the same way. For every single one, you need to put a sketch down. Whatever it is, in this case it's a rectangle, you're going to sketch a rectangle. On your picture, you will put all things that are changing. So on this one it says the rectangle is undergoing changes to its length and its width. It means these aren't constant. All of them or both of them are changing. As as you change the length and the width, two things will change. What do you think changes on that rectangle? Area changes and perimeter. So here, again, we're starting with easy geometry. That's why it's an intro day, because if I start you right off in the medical field with blood pressure the medication and the radius of the artery, and it's too much. So we're gonna start with something really easy. We're always gonna go see what they give me. That's right here. They tell me that I've got a length increasing at a rate. That's a derivative, or a rate of change. I'm gonna use L for length, not dy dx. I'm gonna say dl dt, because this is something changing over time. It's increasing, so I'll put a positive 2 there. You don't need to put the label on it right there. At the end, we need a label, but when you're setting it up, it also given is my width, and it is also increasing, so no negative rates of change right now. That's what you're gonna put down for your given. You're gonna read and see, well, what are they asking me to find? It says, find how fast the perimeter is changing. What do you think I'm gonna call that? dp dt, yeah, exactly, dp dt. Now this notation right here, this single bar, is kind of universal notation for the words at the moment that, or at the instant that. When you draw that, then you go right under here and you say, I'm gonna stop the clock, or take a screenshot of this the minute the length is 10, actually be the second, that the length is 10 and the width is 6. That's kind of notation for that, all right? Now, I need an equation for the perimeter in terms of, and so that's why this is easy, because my perimeter would obviously be 2 of the lengths plus 2 of the widths. You will not be struggling with the equations today. That's not the point. The point is kind of the process. Right now I've done no calculus, but it's actually, we're on step 4. All right, so you draw a sketch, give the rates you're given, the rate you need to find, and an equation that relates those variables. Then, all right, now I'm gonna have you draw a little squiggle down there. I'm gonna have you do it for delta math too. I'm gonna have you set it up, and then over here we're gonna start the calculus. So I need to figure out what the derivative is of the perimeter. So I need to take the derivative of the left-hand side to get dp dt, which means I'm going to need to take the derivative of the right-hand side. All right, so there is my derivative taking. The good thing is the derivatives aren't all that bad. And I mean, you've taken a lot more difficult ones. You just have to be careful right here, because you might say the derivative of twice L is 2. That would be if it was 2t, right? So this one, I would say it's 2. The constant can come out front, but I'm not left with dt dt. What am I left with? dl dt, right? So, and I know I'm recording, so I'm not going to talk to you guys a whole lot, but I do need to look out and make sure you got it. So when I take the derivative of twice L with my variable of change being t, then I have that implicit. Likewise, this is going to be 2 times, and then it'd be dw dt. All right? Once you are done taking that derivative with the chain rule or implicitly or however you want to think about it, then you start plugging stuff in. All right? So I'm just going to go over here and start plugging stuff in. It says I take 2 times, and I do dl dt. That was given to me up here. Okay? When they get more complicated, you're going to be referring to this a lot. You can kind of guess why. Otherwise, you're going to have to read the problem like 3 times while doing the problem. So you do want to pick all the info out before you start. Again, today is intro too, so it's not going to be too complicated yet. All right, but if you page through your notes, you'll see tomorrow we're doing an oil spill. I think we're doing an airplane. They'll be a little bit more pumped up. So again, this 3 came from this guy right here. When I'm all done, I'm at 10. You always have a point for the label on these, always. So you need to go back and decide how you're going to label it. It helps to look at that top variable and say, what would it be measured in? Because your work is eventually going to be pretty long. Well, I just found the rate the perimeter's changing. What would perimeter be measured in? Inches. So this will be in inches, and this is per time. So that would be my time unit in this problem, which is seconds. Now, the one that I told you we were doing in BC when it was changing as an angle changed, right? And if they got 2, right? And if we were doing dr d theta, maybe the radius changing as I increased an angle. Then they would say inches per, and we'd say, well, what are angles measured in here? What, not in here, it would be degrees, but in here, what do we use instead? Radians. So it's always this per this. Almost always time though on the bottom for you guys. We're done with that one. But now we have the exact same problem, but it's different because what we're gonna do now is increase that length. So again, we're gonna have a length changing over time. It's increasing. Length goes on my picture as a variable because it's changing. It only goes on as a number. Like sometimes I get kids who go, it says the length is 10 and they put a 10 on there. You only put a 10 on there if the length is 10 and we're not increasing or decreasing it. We're gonna have some constants, right? Watch this. Don't draw this. One of the big problems that introduces related rates in almost any textbook or any course, and there's one tomorrow, is what they call the falling ladder problem. So a ladder is going to be falling down a wall. What step would change in that problem? Go ahead and give me some. You guys can talk. They can't hear you. What would change as that ladder falls down the wall? There are things changing. It's what? Go ahead. What's changing? The what? The angle is changing for sure. It'd be going shrinking, correct? This angle up here, if I called it alpha, would be growing. So yes, you're right, the angles are changing, both of them, right? This would be changing. Would it be increasing or decreasing? Decreasing. This would be changing. It would be what? Increasing. The area of the triangle would be changing. What wouldn't change? The ladder length, correct? So if they tell you it's a 10-foot ladder, you can go ahead and maybe this is A and this is B. Hey, what equation relates those 3 things? Pythagorean theorem, thank you. You would say your equation is a squared plus b squared. You wouldn't say equals c squared because c is not changing. Constants can go on your picture, right? And in your formula. What happens when you take the derivative of this? What do you get? 0. That makes sense. Because the derivative is a rate of change, and that ladder's length is not changing. Kind of now starts to make sense why constants go to 0, correct? Now, if that wasn't a ladder, but it was an airplane, right? Then the problem's a little different, but oh, my smartboard's being stupid. Maybe it's an airplane flying that way. Now is this length changing? Yeah. Yes, now it needs a variable. Is this distance here changing? Yes. Is that changing? Yes. Are the angles changing? Yes. See what so it depends on the problem. For this one, if the length isn't 10, the length is it needs a variable. The width is decreasing, so I'm going to use not a 2, but a -2. All right? And you don't need to put the labels in the given. It's just to get your poop in a group. The label comes at the end. You can put them on if you want, but then it says, how fast is the area changing this time? So I'm looking for dA dt, and I'm going to call it dA dt so I realize when I'm done I found the area. Because watch when I'm done. If I'm looking for dA dt, you can anticipate what my answer's label is going to be. If you call that dy dt, you're going to forget that y was an area and you're going to label it wrong. Does that make sense? What do we measure area in? Inches squared. So if you label it with something appropriate, it's going to help you label. I'm supposed to start and this at the instant the length is 10 and the width is equal to 6. Next up is my equation for the area in terms of my picture. Area equals length times width. That's the setup. Next, can you anticipate what happens next? I like to draw that squiggle line for what's going next. The what? The derivative. The derivative actually, I call it starts the machine. What's the machine doing? Pulling on the length and squishing the width down. Once you take the derivative, it's kind of like you jumpstart the problem. You get things in motion. All right, so my dA dt is going to be the derivative of the right-hand side. Super important, hopefully, that you understand what's going to happen on the right-hand side. Because what is this function? Product. What rule do you need to use? Product rule, yeah, so now you really need to understand how to implicitly take a product rule derivative. So we would do first, what would I call d second? dw dt. So I really have tried to stress to you guys what you're doing so that I used to say with implicit, really write that down, that the derivative of y squared with respect to x is 2y times the derivative of the guts. What did I allow you to call this when it was done implicitly? Y prime, because you would never lose track of the fact that it was y's derivative by calling it y prime, correct? But when you're doing them in these contextual problems, you don't call that w prime, because you lose track of what's changing. All right, next up. First d second plus second, and then likewise d first would be dl dt. Now I go and I plug everything in. I hope I have it all. There's going to be one we do today where something's missing. But on this one, do I know when I'm stopping this machine? Yes. The instant the length is what? 10. I plug it in. Did they tell me the rate that the width was changing? Yep. Did they tell me what the width is supposed to be when I stop it? Yep. And did they tell me the length's rate of change? Yes. All right. So when I add this all up, I get a negative 20 plus 18. I get a negative 2. What does that mean in the context of this problem? What's happening with the area? It is decreasing, right, by 2, and what's my label? There we go, thank you, inches squared per second. If you're watching the video, you can't hear them, but that was pretty unanimous. So I'm thinking maybe I can pick up the pace a little bit, but let's go take a look. This is a right triangle that has sides with the lengths changing. Now, if they told me it was a right triangle that had a length of 6, or a base of 6, and a height that was changing, then the 6 can go on here. It means all you're going to do is increase this. But it says both of them are changing, they both need variables. You could call them base and height. X and Y actually is kind of reasonable here because this looks kind of x-axis, y-axis, correct? Or A and B because of a squared plus b squared. You can pick. I think I'm going to go with A and B just because I know what's coming in the next part. So it says, the rate of change of the area, oh, I have to go up here. It has sides that are changing, the short side, so that would be my A. So my dA dt is increasing, positive 3. And then it says the long side, so that'd be my dB dt, is decreasing, so negative 5. There it is. This one says I'm supposed to find the rate of change of the area, so again, might as well call that dA dt so I don't lose track of what I'm finding. I'm going to stop this when the short side has grown to 30 and the long side 40. All right? And my equation that relates the two. How do you get the area of a triangle? 1/2 of the base times height, or base times height divided by 2. I like the fraction out front because you're going to want to keep your constants out front. So I'm going to write it as 1/2 AB. And then the squiggle, what comes next? You shouldn't even need to look at those steps. The minute you've got it all set, what do? Derivative. Yeah, you start messing with the area. Okay? So here's what I would also do. Constants, whether they are pies or halves or whatever, always can come out front. So I would write it like this. Not that it's super important today, but when they get a little more involved, if you have constants everywhere in your derivative, it's more likely you're gonna make a mistake. All right, so next step, I gotta look at what I'm taking the derivative of, and again, what is that? It's a product. Yeah, it's two functions changing as time goes by. So it's two functions of t being multiplied. So I'm going to use my product rule. First, and then what's d second? What is it? dB dt, yeah. So first d second plus second d first. And there's no variable match. Again, if that had been t times b, or I don't know what formula would have time times space, but if it did, then you could say it's just A, dt, which is just A. All right, I'm ready to plug. Are you ready? In 4A goes a what? Well, let's see. They told me the short side's going to have to be 30 when I stop this. The rate that the long side is changing, or my dB dt, was a -5. And then plus B, which is what? 40 times dA dt, and I purposely did something incorrectly to warn you to be careful. What'd you say, Rose? Yes, if you left this on the FRQ, it would be wrong, not because you didn't simplify it, because that half was out front. So you've got to be careful. Could I leave that on an FRQ? What do you think? Yes, but I'm going to clean it up. I have -50 plus 120, -30, half of that, -15. Okay? Now, what's my label? If you labeled it, yeah, it's an area changing as time changes. Area in this scenario, was this in inches? Yes, would be inches squared. What's my time unit? Seconds. What does that mean about the area? It is shrinking at that time. Now, same picture, totally different problem. Same picture. Here we go. Same picture. It still has a short side, and it still has the same given. So let's just draw an arrow. The rates are still the same. But on this one, it says, how fast is the hypotenuse changing? That needs a variable. What would be logical? There, okay? So I'm finding dC dt. They'll tell me when to stop it. Still the same instant in time. The instant that the short side, which for me is A, and the long side, which for me is a B. So that's when I'm stopping it. Now I need an equation that relates those three things. What is it? There we go. A squared plus B squared equals C squared. The Pythagorean relationship gets used quite a bit. Like when there's going to be one where someone's flying a kite. There's going to be some airplanes, some nautical stuff like ships and things. So that Pythagorean relationship's fairly common. Let's go over here. What's next? I bet you have it without even looking at the steps. What's next? Derivative with respect to time. So as long as you can think that out, I'm fine. But the derivative of a squared is 2a, but what should I be multiplying it by? D what? A dt. Yep. So it does help if you kind of realize, it does help to write that step out. You don't get any points for it, but it kind of helps you with that chain rule. So it'd be 2a dA dt plus 2b dB dt would equal the derivative on the right, which is 2c dC dt. Are we good? Now I have to go plug everything in. So back to plug and chug. A was 30, right? What was dA dt up there? Oh, I can see it. It was a 3. Plus, and my B is a 40. dB dt was -5. How are we doing so far? Good? 2 times, C I don't know, question mark. dC dt is what I'm looking for. So go ahead and write a dC dt over there. I can't quite fit it in, you guys. I'm on the edge of my screen right here, but here. Right there, write a dC dt. And I would circle it. I'm going to tell you once we get to the harder ones, circle the thing you're looking for. It should be the only unknown. If not, there's 2 things that happen. I have 2 unknowns right here. I don't know the C, and I'm looking for the dC dt. There can only be one. How many? 1, and it has to be this one, right? So it means you either missed it in the stem of the problem, or you're supposed to be able to figure it out from your picture. Would it be expected that you should be able to figure out this length the instant this one's 30 and the instant this one's 40? Yeah, they don't need to give that to you. What are you going to use? The Pythagorean theorem. Or do you recognize that triple? 3, 4, what? 5. So let's just go do C equals 50. I'm not in the business of, why is my smartboard? This is making me nervous because this is what happened to my last one of these. It might be picking up my sleeve though. So it's that, no, it's not. Uh-oh. the end of an era for my new smartboard. All right, that's a 50. So we're gonna go put that right here if you can. Go ahead and erase that question mark. Put a little 50 in there. All right. If you leave that on an FRQ, you don't get full credit. Do you get why? Well, actually, it's got two issues. First of all, you have to isolate your unknown. So this would be what dt equals. You could leave this all undone. With 2 times 30 times 3 plus 2 times 40 times negative 5. All over what? 100. Correct? Could I leave that? What do you think? Yes. I get the answer point. What point wouldn't I get right now? The label. So I have to go back and figure out what was I finding. The rate that C was changing. What would C right here have been measured in? Inches only. So do you see how that really helps with your label? This would be inches per what? Second. Okay? I think it ended up being negative 1.2 last hour, but I'm going to trust you guys to do arithmetic if you had to, right? And we're going to move on to our very last one on the next page. I'm going a little faster because I'm recording. Let me know if I'm going too fast. But so go to the next page, and we're going to do only part A today. On our next page, we've got a cylinder. So you better draw me a picture of a cylinder. It says it's a right cylinder, just means it's not oblique or slanted. So I'm just going to draw a nice cylindrical shape right here. I'm going to decide what I'm doing with it. There's two things that you'll be doing with your shapes. Either changing them specifically, like changing the dimensions of the cylinder, or you'll be filling them with something, or something will be leaking out. So read this one. Am I changing the shape of the cylinder itself, or am I filling it up, or is something leaking? I'm changing the shape itself, okay? So I'm not filling it up. If I was filling it up with water, which you will be doing tomorrow, what's not changing when you fill that up with water? The radius, correct? But if I'm changing the cylinder shape itself, it's like in a machine shop, like cylindrical slugs, like spark plugs and stuff. That's what they do. They put them in machines and they stretch and pull until they get the shape they want, and then the machine spits them out, correct? This machine has been programmed to have the radius grow at 2 feet per minute. So I'm going to put dr dt, and it's this, like it is the thing itself that's changing. All right? So dr dt, and it's growing, so that would be a 2. How about the HDT? Let's see, there looks like they're making a short, fat cylinder out of that slug. That should make sense to you, correct? Because I am increasing the radius and decreasing the height. That's what the machine is doing. All right, I'm supposed to find the rate of change in the volume of the cylinder, like how much steel do I need to make that compressed cylinder. So I'm looking for dB dt. There we go. When am I supposed to stop this machine and have it spit out a spark plug? The minute the height is 10 and the radius is 8. And I had to check right here to make sure when I said the minute one, but I did. It wasn't the second one, correct? Now I need an equation. Anyone here remember how to get the volume of a cylinder? No? Okay, let's go over here. Do you guys remember how to get the volume of a box? What do? You do length times width. Really what you're doing is covering the bottom of it times what? And then you're filling it up with the height, correct? So cover the bottom of this. What would you do? Pi r squared, okay? And then pull it up with the what? Height. Last hour they asked me, will we be given the formulas? That's a really good question, because for College Board, they do have a rule for that. If it's two-dimensional, no. Which means you better know how to get the area of a rectangle, a square, a triangle, the Pythagorean theorem. Those you won't be given. But the volumes, unless it's a cube, you'll be given. What's so funny? What's funny? There's this booger. Zipper down, which is always, you gotta check those two things. Oops, I'm recording. A cube you better know because all the base, the length, the width, and the height are the same. So it'd just be like, if you wanna call it an edge, E times E times E or E cubed. But they would give you this. Do I like that? Not really. I think you should know basic geometric formulas, but if it goes three-dimensional, they'll give you cylinders, cones, spheres, that type of thing. So you don't need to have it memorized. You do, though, need to know how to take its derivative with respect to not the radius changing or the height changing. I'm going to have the time changing, okay? So what do you think I'm going to do with this pi right here? Pull it out front before I take the derivative. It saves me a step. So I'm going to do the derivative over here of r squared h. It actually looks kind of complicated. Like your September self, looking at these when we're done, would be going, I'm dropping calculus. Right? Your September self, it looks complicated, but you should know what this stuff means now, right? So be careful here. What do you think I'm going to tell you? Be careful here. Product rule. Be careful of product rule. Nobody ever seems to just gloss over the quotient rule, but I just had somebody in DC last week, don't write this, because they were working on related rates last week. We had an AB review week, because their exam covers everything. So everything you guys are learning and their new stuff is fair game. So I did have a couple of the 20-some in there say the derivative of this, don't write it down, is 2r dr dt, and I won't call them out on it, times dh dt. And doesn't that look really good? Right? You bring the power up front, and I did do times dr. What's wrong with it? I did the derivative of them separately, correct? That's not what you do with products. So I'm going to circle this, erase it, and do what I do with products. I do first. And what's d second? dh dt. And they knew it too. It's just so easy to gloss, or it's not like they didn't know how to do it. They actually even knew they should have done it. It's just it looks so good when you do them separately that you feel like you're doing it right. And then my next one would be plus second. And what's d first? 2r times what? dr dt. It looks really complicated. It's actually not, especially with you guys so focused. It goes pretty well. Oh no, you're not getting sick, are you?
No.
Okay. All right, here we go. R squared. And don't forget the parentheses. When am I stopping this? When am I stopping it? The minute R is it? I didn't label it, so notice I you gotta label things. I was almost gonna put a 10 there. All right, so it'd be h squared. dh dt was given to me, -3, I think I'll use parentheses. And then plus h, that's gonna be the 10, times the 2, times the r, times the dr dt was a 2, correct? Could you leave that?
Yes.
Yes, if it's an FRQ. You'd lose a point, because what's it's missing? The label. So let's go back. I am going to leave it. I assume you could do the arithmetic. If it's multiple choice, they would have all that cleaned up. But if it's dV dt, what's your label? What would volume be measured in this scenario? Cubic feet. And what's my time unit? Per minute. I'll let you write that down because I ran out of real estate at the end of the screen then. All right, I'm going to just go like this, and we're going to quit. Your assignment is Delta Math, and you're going to do it on this sheet. You might finish, because last hour most of them got into the second set, but I tend to go faster when I record, so they had 5 less minutes. So you might, but I'm going to show you what I want on this sheet. There's 8 problems. They're only on rectangles and triangles, so not even like cylinders. It's just getting the flow of related rates down, and then tomorrow, if you look ahead, tomorrow's examples are pretty detailed. So what I want you to do, oh my gosh, my smartboard's driving me nuts. On your Delta Math sheet, right, there's this. Each of your problems, though, I want you to work with them like that. Over here will be everything you're setting up. What am I going to have you be doing in that second? Like, you're going to kind of split each one of these. What are you going to do in the other part of it? The derivative, and get your answer with the label. So set it up, then do the calculus. Set it up, then do the calculus.
Just like we were doing.
Yep, just like the notes were. Today's lesson really isn't about the answer. All right? So if you can do it faster, skipping steps, don't. I'm going to give you credit on here. The whole reason for this is the steps. Because when they get harder, you can't skip them. So don't. You're gonna want to, because it's kind of easy today. All right, go ahead, start Delta.
Yeah.
Oh, and I should stop recording.